Here are the notes for section 7.4, which is arc length. So we know how to calculate the distance between 2 points using the distance formula, just x2 minus x1 squared plus y2 minus y1 squared, all square rooted. That's the Pythagorean theorem. But what happens if the curve that we're looking at is not a straight line, but is actually a curve? So what we're going to do is break up that curve into lots of little straight lines, use the distance formula over and over again, and then sum those distances, but then make those lines very, very, very small. So it's a limit process applied to lines that become a curve. So some definitions: the difference between the x's we're going to call delta x, the difference between the y's we're going to call delta y, and s, capital S, is the variable that's used for arc length. So if I want the arc length, then I'm going to add up a whole bunch of straight line distances. So difference in x's becomes delta x, difference in y's becomes delta y's, and we have arc length is the sum of the distances of all these straight lines. So all these straight red lines added together approximates the arc length. The trick, the algebraic trick, is to factor out a delta x squared. So there's a delta x squared in the first term, but there is not one in the second term. So when I factor out a delta x squared, there's a 1 left behind in the first term, but I need to put a delta x squared in the denominator. That way, if I were to redistribute this delta x squared, I would get delta x squared plus delta y squared, because those delta x's would cancel out. The next step is to say I've got a square root and a squared, so the square root of delta x squared is just a plain old delta x, and then the realization that this fraction, the squared fraction, delta y over delta x quantity squared, is the derivative. The mean value theorem says that at some point the derivative is equal to the average rate of change of a function. So now that I have a statement that looks like this, 1 plus f prime of ci squared delta xi, and c is some point in the interval of delta y over delta x. So somewhere in this delta x, there's a point where the first derivative matches the slope. Anyways, we can now take and let this delta x distance become very, very, very small. If I let the number of red lines increase to infinity, that makes each delta x very small. And what we have is the limit as n increases, or as delta x approaches 0, of the sum of all those red straight line segments is this statement. This part here is the limit definition of an antiderivative. So now I've got the antiderivative of this function, f prime of x squared plus 1 square rooted dx. If I wanted to do arc length in terms of y's, I would just do c to d, which are y values, the function in terms of y, and dy. So we're going to walk through two examples. The first one says, find the length of the arc on this function between the points 8,2 and 27,17. So the formula, I need the derivative of the function, and then I need to square the derivative of the function. So the derivative is 2x to the negative 1/3. That quantity squared produces 4x to the negative 2/3, or 4 over x to the 2/3. Plugging everything into the formula, I'm starting at an x value of 8, I'm ending at an x value of 27, and 1 plus f prime of x squared is this quantity here. So at this point here, it's set up, and if we're allowed to use a calculator, we just put this into the machine and get a number out. But some of these are no calculator questions, and there's a couple of algebra tricks that you need to practice. So for something that looks like this, get a common denominator. Realize that if you move this denominator, which is a squared value, outside of the square root function, you're going to get x to the 1/3. And then because it's in the denominator, it's x to the negative 1/3. Now you have a setup for a perfect u substitution. If u is x to the 2/3, the derivative of that will have an exponent of negative 1/3. So to make the entire quantity underneath the square root equal to u, produces a du of x to the negative 1/3 times 2/3. I need a 2/3, so I throw one in. I offset it with a 3/2, and now I've got a u substitution all complete. Don't forget that when you do a u substitution, the values at the beginning and the end of your antiderivative change, so these are no longer 8 and 27. Take the antiderivative of u to the 1/2, you get u to the 3/2 times 2/3. Those coefficients cancel out. Replace your u back with your x statement. Replace your values back with x equals 8, x equals 27, substitute, and the final arc length is 13 to the 3/2 minus 8 to the 3/2. The second type of example that you might see is going to look a little bit more complicated algebraically. Again, we want the arc length on a function between x equals 2 and x equals 5. This function looks a little bit different, so taking the derivative and the squaring of that is going to be a little bit more involved. Here's the function. its derivative is this. Changing it so that we have no negative exponents produces this. And at this point, when you have a two-term function, it's probably a good idea to get a common denominator and turn it into a polynomial over a monomial. So the f prime of x squared is this statement here. Plugging it into the arc length formula produces this, and now the algebra tricks are the next step. So squaring all this out produces this, and a couple things you got to be careful. Some common mistakes are if you have x to the 8th squared, remember that a power to a power gets multiplied. X to the 8th times x to the 8th is x to the 16th. Okay. Top is a binomial that gets multiplied out to a trinomial. Bottom squared is this. Now to get a common denominator, 1 is going to become 4x to the 8th over 4x to the 8th. Add your like terms and you get this statement, which factors into this. So the trick for a problem that starts out with these two terms here is that if you do the algebra correctly, you should wind up with a numerator that's a squared quantity and a denominator that's a squared quantity. Square rooting and squaring cancels out, and now you're left with the antiderivative of a polynomial divided by a monomial, which we can do if we just separate into two separate things, x to the 8th over 2x to the 4th and 1 over 2x to the 4th. We get these two statements. Term by term anti-differentiation produces this. Again, substitute in your x values 2 and 5, and you get this statement, which is a little bit messy to figure out by hand, so we're just going to leave it as this statement here. Okay, that's it. For arc length, there's pretty much two types of algebraic situations that you got to be on the lookout for. Just try and remember the tricks for those two, and you'll be fine.